Okay, good morning everyone. Thank you for joining us. This is our presentation on the design for a battery electric vehicle suitable for the 2026 Shell Eco Marathon. In this presentation, we'll start off by giving a background into what the Shell Eco Marathon is and why this competition is so important for students. We'll then dive into the purpose behind our project and why we chose it. I'll then go over the design of the body. Adam will cover his chassis design, and Bryan will go over the front subframe and steering. We'll then end off with the final conclusion and vehicle assembly that we created, give our future recommendations on this project, and give our thanks.
All right, hello everybody. You're probably wondering what the Shell Eco Marathon is. The Shell Eco Marathon is an international competition where engineering students all around the world get together as teams to design and manufacture ultra energy efficient single passenger vehicles. Competition categories include internal combustion, hydrogen fuel cell, and battery electric, which is the category our vehicle is designed for. Teams are driving a fixed number of laps around the track, and after each valid run, energy efficiency is calculated and ranked. Awards are given to the highest performing teams for efficiency rather than speed or placement. The goal of the competition is to get engineering students involved with sustainable mobility and real-world engineering problem solving. These student competitions are important because they teach the required teamwork experience that builds practical engineering skills far beyond the classroom. Some previous competitors in the competition include right here at Red River College and also the University of Manitoba.
So Red River College used to have a Shell Eco Marathon team. Unfortunately, during COVID, it was shut down despite our industry support. And with our previous team, we actually placed 5th twice. So with our project, we're hoping to get Red River back into the Shell Eco Marathon as a competitor. We went to go look at our previous design, which is shown at the top photo, and you can see Jeff, he's sitting in the cockpit and his head is completely sticking out of the car. And that's one of the flaws we'd like to change with the new design. You can also see the door and windows lying on the ground. They were held on with magnets, and these magnets could constantly fall off during a race, which is something else we'd like to change. And on the bottom photo, you can see the steering, and the blue handles the steering wheel where you would move back and forth using a tiller style of steering. With the new design, we hope to change that back to a conventional style of steering.
So starting off with the body design, I first went over the overall dimensions of the body and designed a more accommodating cockpit that could fit a larger range of drivers. I'll then cover how we met our aerodynamics and the panel stiffness requirements that we set out. I'll then cover how I integrated with the front subassembly, and finally I'll go over how we solved the canopy retention issue. So starting off with the cockpit, we set out to allow heights from 5'3" to 5'9" based on average heights in Canada. Luckily, we have a perfect volunteer that's right in the middle at 5'6". I measured her body dimensions and was able to create the digital mannequin seen on the right. And we were able to determine a comfortable seating position. I know this position doesn't scream comfortable, but we tried it out ourselves and it was not so bad. So using that digital model, I then scaled both up and down to get our suitable driver range of 5'3" to 5'9". And this also made all of our designs more seamlessly work together. Putting them all into the same position, I was able to use elliptical curves around the models to create our desired body shape. The rear compartment was assumed to be roughly the same size as the previous RC vehicle, since our designs didn't include any of the electrical or the drivetrain components. Next up is our aerodynamic requirements. We set out to have a drag coefficient of around 0.3. This is seen in most modern production vehicles. And we assumed a maximum speed of 35 kilometers an hour, just based off videos posted online and old interviews of previous competitors. So with the first iteration, it had a drag coefficient of 0.33 without doing any prior testing. So after seeing this, I created splines for the front and rear to give more angle for the air to transition smoother over the top of the vehicle. This lowered the drag coefficient down to 0.24, meeting our requirement at 0.3. And I forgot to play, there's the animation. That gave us drag coefficient of 0.24. Next was the panel stiffness. So I assumed that we could use carbon fiber epoxy composite. This is by far the most widely used materials in the competition, and we have these materials available here at Red River. So starting off with just 4 plies for the entire body at 0 degrees, 90, 45, and minus 45. I used FEA simulations and the pressures gathered from the CFD simulation. This gave a deflection of 2.7 millimeters for the body panels, and we wanted to keep this under 1 millimeter. So after consulting with our instructor Serge, he recommended doing a 3 millimeter thickness along these large, low curvature side regions. After adding this foam core, the deflection was brought down to just 0.73 millimeters. Next up is the front subassembly integration. Once the front subassembly was completed, I created 1 centimeter offsets around all the front subassembly components and created cutouts on both sides of the vehicles. I then used our CAD assembly to move the steering from both the left and right extremes. This ensured that there was no collisions with any of the steering components or the body panels. Lastly is solving the retention method. So going back to the wind tunnel simulation, it gave us a lift force that was created by 2 things. The first thing is the wind. The wind traveling over the vehicle is a lot faster than under the vehicle, and which creates lower pressure on top of the vehicle. That was part of the lift force. The second part is the vacuum or low pressure region seen behind the vehicle. This low pressure region increased the lift force to 4.4 newtons, and we set out to attach the body to the chassis with 2 times this amount to account for variations in wind. So with this retention requirement, I then looked at 3 viable components. This consisted of a locking quick release pin, friction fit latch, and Velcro tape. After comparing the weight, cost, and ease of integration into both the body and chassis, using a weighted matrix determined that the friction fit latch was the best solution. Using just 2 of these latches gave us a retention of 44 newtons, 10 times than what was required. Placing one of each of the latches on either side of the vehicle about the center of gravity meant that the driver could unhook the latches and maintain balance with the body. And I selected an oval handle for the inside of the vehicles and a recessed handle for the outside. Doing a quick hand calculations using methods taught in our strength and materials classes, it was determined that the bearing stress seen at the handles and latches is only 1 megapascal. This is 500 times lower than the stress for the cured laminate, so nothing will break there. Some future recommendations I have for the body is to further optimize the shape. We assumed that the wheels would sit outside the body and chassis. This was done so all 3 of our designs could be completed in parallel, but now that we have the CAD assembly, I think testing whether the wheels inside or outside is more beneficial. Next is a formal material selection for the body. Instead of assuming carbon fiber and foam core, it should compare with fiberglass, fibric, and perhaps alternative cores such as honeycomb. And also for the windows, a formal material selection should be done for the windows. The shapes you see above is from the previous RRC vehicle, and a formal visibility study wasn't done to confirm that the windows follow the most up-to-date rules.
Alright, so diving into the chassis design, the following objectives were considered. First one was safety. I would not want to put my mannequin friend here in any sort of danger. So the chassis needs to be able to withstand the weight applied from the driver and the weight of all the components inside the vehicle. This is to ensure safety, and then it also needs to ensure that it won't crumple into the driver in the event of an impact or collision. The next was weight. The goal of this competition is to be as efficient as possible, so the chassis needs to be as lightweight as possible. Moving into manufacturability, the chassis has to be able to be manufactured here at the college with student knowledge obtained from courses such as machine design and fabrication methods. And for strength, like I mentioned for safety, it needs to withstand the applied static loads as well as an impact collision at an assumed driving speed of 35 kilometers per hour. This value was determined from previous cars' reported top speeds with a safety factor of 2. And lastly, the Shell Eco Marathon rules need to be adhered in all aspects. This includes In the final design, a carbon fiber composite layup is implemented, which provides an optimal balance of structural performance and weight for the Shell Eco Marathon chassis. As you can see, it consists of 4 plies of carbon fiber on both sides, and then the foam core is 30 millimeters, and this is encapsulated by the carbon fiber. And I also selected this material just due to its availability here at the college in the materials lab. Based on the design objectives mentioned earlier, multiple chassis revisions were made throughout the design process. The first revision in the top left here is very box-like, and I wasn't able to get this rear wheel mounted inside the chassis, which is an unconventional design when compared to previous cars. And it also just has too many sharp edges. So for revision 2, I used arcs and curves to design a more round-shaped chassis, and you can see the rear wheel mounting is now inside the chassis. The only issue with this revision is along the bottom edge. It's still very sharp, and that actually does not follow Shell Eco Marathon rules. There's a rule in the rule book that states no outer radii can be sharp, and it has to exceed 50 millimeters. So in the final design here, a 50 millimeter round was added all around the bottom edge of the chassis to adhere with that rule. One last thing that was changed on the chassis is I added a 3 millimeter edge indentation along the entire edge of the chassis. This just gives the body a solid place to rest on when it's lashed in place. A static load analysis was conducted on the chassis to determine if it can handle the weight of the driver and the other components. A 2.2 kilonewton load was applied at the center of the chassis where the driver will be sitting. And this is based on the weight of 83 kilograms for the driver. This comes from Canadian standards, and a component weight of 30 kilograms, which is based on previous cars. The chassis was constrained where the front subframe mounts and the rear wheel mounts to the chassis. The initial chassis design mentioned earlier barely passed the flexion requirements with a safety factor of 2, suggesting a need for improvement. So the final chassis design added a 50 millimeter perimeter edge all around the chassis as shown, and this increased the stiffness of the chassis by a factor of 6. The results now show a total max deflection at 1.3 millimeters and max stress at 2 megapascals. So essentially, my mannequin friend could weigh up to 2,000 pounds and the chassis could still support it. A front impact simulation was also conducted on the chassis. The objective was to evaluate the chassis' ability to resist a frontal impact at a speed of 35 kilometers per hour without excessive intrusion into the driver's footwell and without catastrophic damage to my sandwich panel. The FEA results yield a max stress of 4.7 megapascals, which is significantly below the ultimate stress of carbon fiber. This means under the applied crash scenario, the chassis is over 100 times stronger than the breaking point of carbon fiber. So in short, if my chassis hits a wall at 35 kilometers per hour, the wall should be more worried. The displacement result was a maximum total displacement of 17 millimeters. This displacement is well within the 100 millimeter requirement with a safety factor of 2. With a displacement of only 17 millimeters, the driver won't even spill their coffee. You can't drink coffee in the car. The following recommendations can be made on my chassis design. First one being to further optimize the panel thickness. As mentioned in the FEA results, the chassis design exceeds requirements in both static load FEA and impact simulation FEA. This opens the possibility of the chassis being over-engineered. By optimizing panel thickness, such as using lesser plies or a thinner foam core, we can meet these requirements more closely while making the chassis overall weight reduced. And second, we could conduct a full assembly stiffness check. We know that the chassis meets all the requirements on its own. However, when the subframe and body and all the components are mounted to the car, the chassis results may differ. So the final assembled vehicle can behave differently due to load path changes, joint flexibility, fastener tolerances. And lastly, we should complete a rollover analysis. We know the chassis can handle impact loads, but can it safely protect the driver in the event of a rollover still needs to be determined.
So with the design of the new subframe and steering system, I wanted it to follow some rules, being lightweight and completely manufacturable at Red River College. It also must follow all the Shell Eco Marathon rules, which include a minimum track width of 500 millimeters, a height to track ratio of 1.25 or less, and it must also be able to withstand all the design loads. I started the walk by brainstorming concepts and sketching them. These concepts all differed with their design structure and their driver seating. From these, I went to a decision matrix, and I compared these using driver entry or exit speed, repairability, how manufacturable it is at Red River College, and the driver comfort. Concept 1 came out on top with a score of 9.7. So revision 1, highly based off concept 1, used 4 spherical bearings, you can see on the left photo. These bearings were mounted directly in the subframe, and they are used for the knuckle pivot points. So the knuckles being machined aluminum would have to be very large, which would increase cost since subframe would need to be mounted in double shear. The lower spherical bearings were also mounted in the center of a tube, so extra tubing had to be applied there to ensure the bending force was supported. So with revision 2, I moved to rod ends mounted directly in the machine knuckles. With this revision, I was able to make the knuckles a lot smaller, and I could completely redesign the subframe. You can also see in the last photo here on the right, the steering was added and it's mounted very high on the subframe. So with that, I went to the CAD assembly, I put the steering in, and I did clearance checks with the driver's legs. As you can see in the top left photo, the steering has very little clearance with the driver's legs. The pink would represent a 5'3" driver. So with the final revision, I moved the steering down to the bottom of the subframe to ensure there was no collisions during use. I moved on to hand calculations to find loads to ensure all the parts will withstand their forces. I started off with all the forces on the subframe, which include the vertical force and the backwards force towards the rear of the car during braking. These forces were used to ensure the subframe mounting bolts could withstand the loads. I then did calculations for the steering loads to ensure the rod ends for the steering and the drag links would withstand all the loads, including buckling and stress in the drag links. Finally, I moved on to the subframe. The subframe first was analyzed as a 2D truss. This was to ensure I could calculate this by hand, and I could compare it to a FEA. I start off by finding the forces in every single beam, and then using the selected material in the material selection, which was 6061 T6 aluminum, I found the stress in each beam. I compared this stress to the stress in each of the beams into the FEA, and this validated the stress path in the hand calculations, closely matching. Finally, I did a final FEA. This FEA used all the forces on the subframe that would occur during a race. A mesh refinement was done to ensure the mesh size had no effects on the final results. Stress and displacement, they flatlined very early, with stress peaking at an average of 33 MPa and displacement peaking at 0.266 millimeters. You do see a stress singularity in the stress and safety factor, and that was not included in the averages. And with the safety factor of 8.45, the subframe can withstand all the loads that's been designed for. Some recommendations I have for this would be include steering stops. As of right now, the tires could have a possibility of oversteering and hitting the body or causing an accident. Steering geometry could also be optimized to ensure the car will track straight on its own, and it could also increase its power usage or decrease its power usage. Finally, an impact test could be done to verify its strength during collisions or curb strikes.
So in the end, we had all vehicle components that we designed fit seamlessly together, meeting our own performance requirements and also complying with all the rules of the 2026 Shell-Eco Marathon. We were able to solve those 3 key issues we saw in the previous car. We made the cockpit much more accommodating, the retention method is far more reliable, and we used a more intuitive steering design. The vehicle was also designed minimizing weight and having all custom components be manufactured right here at the college by students. This further adds educational value to this project.
Alright, so wrapping things up here, we would like to acknowledge Cassie Davidson for being our advisor throughout this project. She helped us consistently with technical report writing and avoiding project scope creep. Secondly, we would like to acknowledge Nino Calderola for all the CAD and FEA advice when we ran into issues during design development. And also, thank you to the rest of the MET faculty for giving advice involving random questions throughout this project. And lastly, we want to thank all the co-op employers who gave us great project management skills and real-world engineering experiences throughout this program. And thank you so much to everybody for being here today and listening to our presentation. Now open the floor for any questions.
So you said one of the big issues with the body was the lift force and your low pressure system behind as you went. Was there any thought into maybe adding some vortex generators or underbody designs to increase?
One thing I should have mentioned at the beginning is one of the Shell Eco Marathon rules is you're not allowed any external appendages.
Oh.
So any fins or any sharp points. None of that.
Okay, fair enough, yeah.
Josh?
Looking into the latch selection between the lock pin, the Velcro tape, and the groove, for the one that you had selected, was that something that you had picked out or a 3D print design?
So that is selected off of Mastercam, or no, McMaster card. It could be 3D printed. I actually did 3D print it in order to test it out for our sort of makeshift model that we have out on the table, scaled down 6:1. So I think it definitely could be 3D printed, but this is just based off standard hardware selection. And something I forgot to mention was those friction fit latches, they're only roughly 2 grams each and under $2 each, so that's why I wanted the matrix.
Yeah, because I was looking at the design on it and I thought it was something else. I had seen that.
Yeah, go ahead.
Just wondering if you had access to the previous designs from previous cars to base where you were going, like was their actual design, not so much parameters, but their assumptions of what they work with, and will yours be available for future classes?
Yeah, so for the previous car, all we had was what you saw in the pictures. It's been stored in a shed. We brought it out and it's in pieces. It's really unfortunate. We also couldn't get any old CAD models or any designs that were done. So we submitted our entire CAD package and assumptions made with our report for the future MET students.
Go ahead.
On that rule, we're not allowed to have any extruding appendages on the body. Does that mean you wouldn't be allowed to cover up the front wheel wells where there's cutouts? Would you not be able to cover that with more body work just to reduce drag?
Yeah, some of the bodies they increase the composite material to surround those. We didn't do that to cut material costs, and it's also not a necessity. We assumed since it's such a low speed that there wouldn't be too much drag created by the front subframe. And as I said before, with only about 2 months to work on the design, we had to all work in parallel, so we focused on just the body design for everything.
Hey?
Did you ever consider any alternate positions for the driver, like if they were lying flat on their stomach, like the Liew?
That's not allowed. It has to be feet forward.
Okay.
Yeah.
And Bryan can talk about his front subframe design.
Yeah, so there were some, the designs had different driver positioning. Some had lens through openings, and these were taken from ideas from videos of other eco-shell marathon cars. With that being said, there was a factor in the Shell Eco Marathon rules with a minimum driver exit time.
Oh.
So that's why I did not go with something like that.
Jason?
Did you consider putting the driver farther back at any point in the design?
Initially, we actually had the driver more forward on the car, but based on just keeping the center of gravity on the center of the vehicle, we kept it where it was.
Another thing is we selected the 3-wheel configuration because this is the least amount of wheels you're allowed by the rules, and you need to have 2 front steering wheels. So this is the lightest configuration. So making the rear wheel with 1 drive wheel, one drive wheel, and having all drivetrain components back there.
Better?
Did you do a material selection for the steering assembly, like the 6060?
Yes, yeah, I did. I didn't have time to talk about it. There was a full material selection done. I So I used Young's modulus, density, yield strength, how manufacturable it was at Red River, cost, and fatigue strength. And there isn't one for aluminum, but there is some assumptions made using, I looked at an SN cycle table, and its fatigue strength was above what's needed at 10 to the 5 cycles.
Okay, thank you so much, everybody.